Hello class, this is Professor Finan. Today's lecture is lecture number 3.1, and we will be working on the whiteboard. We will show you the linear least squares derivation. And so we introduced last class that there are both linear models and nonlinear models and non-parametric models, but the vast majority of regressions use linear parametric models. And probably the most common solution technique is called linear least squares, or sometimes it's called ordinary least squares. So today we're going to do the derivation for the linear least squares. And so just as a quick review, in a linear parametric model, we assume that the functional form y equals some function of our input vector x, which can be multivariate, and then some vector of our fitting coefficients beta. And so if we expand this out, this would be beta naught times phi naught of our vector plus beta 1 times phi 1 of x plus then plus beta m of phi m of x. And if you remember, we call our phi of, I'm going to call them phi of j of x. These are what I call the regression function. These are the regression functions, which they can be any function of our input parameters x. Okay, so that they could be polynomials, they could be sine functions, exponentials, logarithms. It can actually be any function of x. But the fitting parameter, we call this a linear model because the fitting parameters, the function f is a linear combination of the betas times our regression functions. And so our fitting coefficients, which the regression is solving for the optimal values of, they do not appear inside the regression functions phis. And so when we do the experiment or the computer simulation, we collect data. So for an observation, yi and xi, we can define what's called the residual. The residual is fine. I'm going to use Ri equals, it's yi, our measured output variable or our measured independent or dependent variable, minus our regression function. Well, but our regression function evaluated at our input xi, comma beta. And so this equals yi minus, and I'll put in brackets, then our expanded regression function, beta naught, phi naught of x, plus all the way up to beta m, phi m of x. And so that is our this is called the residual. And then using vector notation, so we can do using vectors, I'm going to define our vector beta. Let me define over here our beta is just a row vector of our coefficients, beta naught, beta 1, and then beta m. And so this has m plus on beta. Our vector beta is a row vector containing m plus 1 fitting coefficients. So using vectors beta, and now we're going to define our vector phi equals, once again, it's going to be a row vector containing our regression function. So phi naught of x, but this is going to be our regression, our vector theta is actually going to be our regression functions evaluated at the sampled input parameter values, okay? And then phi of m, but evaluated at xi. And so we can now rewrite our residual is yi minus our vector phi, but we're going to use the transpose. So if you take a transpose of a row vector, it turns into a column vector times or dot product with our vector of betas. And so that's just using, and this is where, and t equals the transpose. And so once we, so this is the definition of our residuals. And remember, our data points we have our, we have, I goes from 1 all the way to n. It's our number of our observations, or it's the number of data points in our data set. And so then we can define what's called the sum of squared residuals. And this is for let's define this as S equals, now the summation of from I equals 1 to n is the number of data points in our data set. Ri squared. And so that's for n data points in the training set. And so those are some of our basic equations. So I'll give you a moment to write all of this down. And so now the next step is the actual linear least squares algorithm. So the purpose of linear least squares, so linear or ordinary least squares, the purpose is to find the fitting coefficient beta j's for j equals 0 to m, to find the beta j's that minimize so you want to find the fitting coefficient beta j's that minimize the sum of squares s, that minimize s. So now, and so now we have a minimization problem. And so I will write this as the min of s, which s equals our summation of I equals 1 to n of our Ri square, our residual square. And so how do we find a minimum of a function? The minimum of the function occurs when the derivatives of that, for the first order derivatives, are equal to 0, either indicating a local maxima, a local maximum, or a local minimum. And so the minimization of x, we have to take the partial derivatives. So it's the partial derivatives of s with respect to beta j. And then using our previous definition of s, let me just write out s here again. So, okay. So this would equal 2 times, now the summation of I equals 1 to n of Ri, now times the partial derivative of the residual with respect to beta j. And then we set this equal to 0 because we're doing a minimization problem, and this is for j equals 1, or j equals 0, 1, all the way to m for each one of our coefficients. So we're actually going to have m plus 1 equations. And so now, what is the partial derivative of our residual with respect to beta j? So that's the next step. And so the partial derivative of r, or actually this should be ri. So the partial derivative of ri with respect to beta j, this would equal the, there should be, so this is now negative the partial derivative of our regression our assumed functional fit, with respect to beta j, which this equals then just negative our regression function j evaluated at input x of I. So we're just applying the chain rule of differentiation from our definitions of the sum of squares and residuals. Because remember, our function f is a linear combination of the beta j's times the regression function. So the beta j is just a term out in front of the regression function. And so now this gives us a system of m plus equations. So let me just draw a line. And so now we're going to have a system of m plus equations. And so it's going to be -2 times the summation of I equals 1 to n of yi minus, now our vector phi is the transpose times beta. So our partial derivative is 2 times the residual. This is the definition of the residual. Now times, this would be phi naught of xi, and this equals 0. Which equals, so I'm going to expand this out, -2 times the summation of I equals 1 to n of, I'm going to do this in brackets, yi times phi naught evaluated at xi minus and this should be, remember our vector phi, our vector phi, it has the regression functions phi naught to phi m evaluated at input xi. And so we need a subscript I here. Let's see. And that's the transpose times our dot product with our vector of betas times phi naught evaluated at xi. And then we need to do this for each one of our regression functions. So it's -2 summation I equals 1 to n yi minus phi I transpose times beta times now phi 1 evaluated at xi, which equals 0, which equals -2 our summation I equals 1 to n yi times phi1 of xi minus our vector of regression functions in the transpose beta phi1 phi1 of xi, close the brackets. And now I'm going to do the dot, dot, dot. And now it's -2 summation of I equals 1 to n of yi minus our vector again, beta, times phi of m. And so there's going to be the other phi2, phi3, phi4, etc., all the way to phi m, evaluated at xi. This equals 0, which equals the -2, and the summation I equals 1 to n times yi phi m of xi. And so this is where we have, this is a system. So this is a system of m+1 equations. And so the next step is we can more compactly represent this system of equations by using matrices. And so next we will, we're going to define a matrix X, I'm going to call this the X matrix, with entries xij equals the regression function j evaluated at input so the entries of xij is the regression function j evaluated at input I, at our sampled input I. And so if we write out the whole, I'm not going to write out the whole matrix for you. This will be theta naught x1, theta naught evaluated at x2, and then this is theta naught evaluated at xn, because we have n data points. And then so our second column, it would be theta 1, or I'm sorry, phi of 1. Data point x2 and x1. And then now this also goes on all the way. So this is our regression function, phi of m, evaluated the first data point. At the second data point, all the way down to at the nth data point. And so here you can see this is our X matrix. And so this it's an n by m matrix. So n is our number of data points. M plus 1. M plus 1 is the number of our fitting coefficients. And so I'll give you a minute to write that down, and I'm going to erase the board here. And so next we can also write that we're actually going to need the transpose of this matrix. So the transpose equals the phi naught, phi1 down to phi of m. And this will all be evaluated at x1. So I'm just going to write out for you the transpose of the X matrix because we need the transpose in the next step. This is theta naught evaluated at x2, theta 1. And then we expand the matrix out, theta naught xn and so you can verify that this is our X matrix here, and so the transpose takes this form. And so now, from our system of m+1 equations, which has all of the partial derivatives of our sum of squares of residuals, this system of equations can be written. And so the system of the m+1 equations can be written, expressed using the vector and the matrix notation. And so now it becomes -2 X transpose times our vector Y. And remember, Y, our vector Y, this is from the earlier lectures, is just it's a row vector containing our output variables from our data set. So Y1, Y2, Yn. Plus 2 times X transpose, or X matrix transpose, now times the original X matrix times our vector beta, which is that, once again, the row vector containing our m+1 fitting coefficients. And we set this equal to 0. And if we rearrange this equation, we get X transpose times X times beta equals X transpose times Y. And remember, we're trying, the goal of the regression is to solve for the optimal fitting coefficients beta. And so here you might remember that in this case, this X transpose X is a m+1 times m+1 matrix. And this is a symmetric matrix. It's a symmetric matrix, and it's invertible. And it's an m+1 by m+1 matrix. It's a symmetric matrix, and it's invertible. And so we want to solve for our betas. So we can write this as X transpose X to the -1. That means this is the matrix inverse. Remember, X transpose times X is another matrix. It's an m+1 by m+1 symmetric matrix. And so we can take the inverse of that times X transpose X times beta, which equals, well, we have to multiply both sides by the inverse. X transpose X, the -1, the inverse, X transpose times Y. And of course, when you do from the properties of matrix, for example, the matrix A times the inverse of A equals the inverse of A times A, which equals the identity matrix. So we're just using some of those properties of the matrix inversion. And so now we actually get a closed form analytical solution for beta. So beta equals, so this just becomes the identity matrix, the vector times the identity vector, a vector times the identity matrix just returns the vector. So beta equals, and if you remember here, y is, y has n data points. The X transpose, so this is the X transpose matrix. This is a, what we have 0 to m. So this is a m plus 1 by, but then we have x1, x2, all the way to xn. So this is a m plus 1 times n matrix. Y is a column, a row vector of length m. And so this returns a m by 1 and an m by 1 row vector. Then we multiply that by the inverse, which returns another m plus 1 vector. And so all of the dimensions of the matrices and vectors are preserved here. And so now we get, it's just X transpose times X, so it's the inverse times X transpose times Y. And so this is the final result of this is the least squares or ordinary least squares regression algorithm. This is how you solve for your fitting coefficients beta. And once again, this y is a vector of the n output data points, and then this X matrix, you have to build it. You can assume any functional form for the theta naught all the way to or phi naught to phi m. And so this is why the vast majority of regressions that have been done since the early 1800s use parametric regression, specifically linear regression, because this is a closed form analytical solution. And especially if you choose, if n is small enough, and also if m is small enough, for example, if you use low order polynomial fits, you can actually perform this matrix inverse by hand. And that's actually what was done until basically the 1950s, and actually up until the 1970s. You would have, unless you had access to computers, you would have to perform these matrix inverses by hand. But still, this is a closed form analytical solution. And that's the key point of the linear least squares, or sometimes called ordinary least squares algorithm. So I'll just give you a moment to write all of this down.